All right. So there's some other important things that we need to talk about for simple harmonic oscillators, and that is the equations of motion. And there are equations of motion for any type of physics when something moves. And these equations of motion are pretty important for describing the motion of really any object, but they are the position as a function of time, the velocity of that system as a function of time, and the acceleration as a function of time. There are other ways you can think about these equations of motion as being the momentum and the energy or something like that as function of time, but they're all equivalent. But what we're familiar with is position, velocity, and acceleration. So that's what we will consider for now. Um, when I think about this spring system, I have a spring that oscillates. And if I think about the order of things that happen, let's say I start by I start by stretching it to some positive A, some positive amplitude. Um, and then I let it go, and it goes back through zero, and then it hits the other end. It turns around, comes back, and just oscillates back and forth like that, right? So at position zero, um, my function x should be equal to my amplitude. So I shouldn't say it's actually x of zero times zero is equal to a. Furthermore, x of any time, or x of the period, x is a function of t, capital T period, is going to also give me the amplitude. And if I plug in 1/2 of the period, I should get my negative amplitude, right? Because if I start off at 0 time, I'm at A, I go through half of the motion, which takes half of the time, and now I'm at my negative amplitude. And then it goes back to the positive amplitude and over one full period t. So halfway through that period t, I should be at negative A. One more thing is that this x of n times t, where n is just any integer number, whether it's 1, 2, 3, or negative 1, 2, 3, or 4 or 5, or whatever, any integer number, I should get a plus or minus a, depending on what n is, right? So this is the periodicity, is that after every t, or 2t, or 4t, or 73t, or whatever, as long as it's an integer number times t, if I plug that number in for time, I will get either plus or minus a, right? So that is something that we've seen before, and maybe we're not quite putting it together yet. So let's maybe draw a graph. So here's my t-axis, my horizontal axis, and my position axis will be my vertical axis. And again, I have to start off at some amplitude A. If I don't start off at A, if I start off at my position 0, what happens is that there's no spring force because we're at the natural length of the spring, and so there will be no oscillations whatsoever. So if I do any sort of motion in my simple harmonic oscillator, I have to start at positive or negative A. And just for argument's sake, we'll say we're starting at positive A. It's then going to go through to some 0 position, and then it'll go to some negative A, and then back up to a positive position. And when it reaches that positive position again, our time is capital T. So now maybe you can see that this is probably going to be something related to a cosine function, right? Okay, well, that's great. The other thing is that if I look at x as a function of time, and I think of it as being maybe a cosine theta situation, if I plug 0 in for theta, I would get 1, right? Okay, that works. So if I plug in 0, I would get 1, but I don't want to get 1. I want to get my amplitude A. And so our cosine function should actually not just be 0 or cosine theta, it should be my amplitude times cosine theta, so A cos theta. Now, if I plug in 0, I would get cosine of 0 is 1, 1 times A is A, and that satisfies that condition. If I plug in plug in capital T, I would get cosine of the period is going to be cosine of 0 or 2 pi or 4 pi or whatever is going to be 1 every time. And so I get 1 times A. Furthermore, if I plugged in T over 2, which would be similar to saying cosine of 1/2 2 pi, that would be cosine of pi. And so I would get negative 1 times A was negative A. And so all of that matches up what we said here about these 4 conditions at the top. But there's one more thing, is that this has to be a function of time, not of some number of radians. So if I think about theta, I can kind of maybe work something out. And if I remember from uniform circular motion, we said that omega is equal to theta divided by time, so angle over time. And then I can solve this for theta, and I would get theta is equal to omega times t, which I can then plug into my cosine function, and I would get x of t is equal to a times cosine of omega times t, where omega is the angular frequency or the angular velocity, angular speed, really. Okay, but then if you remember from the last equation, we said something about omega. We figured out what omega was. Not last equation, the last video, we figured out what omega was, and it ended up being something like the square root of k over m, right? We also have that f was 1 over 2 pi times the square root of k over m. And we also have actually, let me just double check that it was k over m, not m over k. Yeah, it was k over m. And then we had that our period t is going to be 2 pi times root m over k. And I can plug all these, stuff in, and what I can ultimately get is that my x of t is equal to either a cosine omega t or a times cosine square root k over m times t. It's also equal to a times cosine of 1 over 2 pi times square root k over m times t. It's also equal to a times cosine of 2 pi times root m over k times t, all these things. But ultimately, it's just basically saying that our function, we can call it omega t, and then we can do all our replacements with either square root k over m, or we could call it 2 pi f times t. We could call it 2 pi over capital T, the period, times t. Lots of different things can go into this, but I think the main equation that you should be aware of is either this one, or I think on the AP exam they give you x of t is equal to a times cosine of 2 pi f times t. That's what's probably on your equation sheet for the AP exam. So that is our position function, and it works out really well because it gives us the values that we're looking for. It's negative when we want it negative. It's positive when we want it positive. It works out just fine. But that is our position function. So let's move on to our next function, the velocity function. Now, if you are I'm making this video and I'm going to post it to both the AP1 and the APC classes, so bear with me. We're going to do both things all kind of at once. But our velocity function happens because it's basically, for APC folks, it's the derivative of our position function. So I'm going to go ahead and do the calculus-based stuff. So if you are a AP1 person, you can kind of just skip ahead. But if you're an APC person, this might be kind of useful for you. If you remember, our velocity as a function of time is equal to the derivative of x with respect to time. So plugging in my x function, I would get d dt of a times cosine omega t. Actually, let me make it in line with your equation sheet. 2 pi f times t. Actually, no, let's go back. We'll do omega t because it's easier to write. So we get the derivative with respect to time of cosine, or a times cosine omega t. A is a constant, so it can come out front. We get a times the derivative of cosine of omega t. I can do a u sub if I'm really interested in it. It would be u is equal to omega over t. And then my du is equal to omega times dt. So then I could replace my dt with du divided by omega. And so I get a times my d dt, which we're going to call d over du divided by omega, times cosine of u. Doing some simplifications, omega is down in the bottom of a fraction, so it's a fraction of a fraction. That means we take the omega, we flip it, we multiply it to the top. It's also a constant in time, and so we pull that out as well. So what we get is a times omega times d du of cosine u. And then our derivative of that becomes a negative sign. And then I can replace my u back with my omega times t, and what I get is my final function of velocity v of t is equal to negative a times omega times sine of omega t. So there's my velocity function. Furthermore, we can figure out our acceleration function pretty easily as well. Furthermore, I can figure out my acceleration equation by just taking the derivative of my velocity function with respect to time. So that would be d dt of negative a omega sine of omega t. And what we get from that, again, is just going to be a negative a. We'll get a factor of omega out front, just like we did from the previous derivative. So we get minus a omega squared, and then our sine becomes a cosine omega t. So those are my equations of motion for the APC people. For the AP1 people, if you're still there, the process that we have to go through, since you don't know how to take a derivative or what that means or what that represents just yet, we'll have to be a little bit more careful. So our position function, to recall for AP1 people, x of t is equal to a times cosine of omega t. If I want to think about my velocity function, a couple things happen. If I stretch and compress a spring and then release it, the system will move from rest, right? So an important point is that v of time 0 should be 0. When I have completed a full oscillation, I am back at the beginning position, and so my v of any period should also be equal to 0. Furthermore, my maximum velocity should occur when I'm at my equilibrium position, which happens at t over 2. Or sorry, not t over 2, but t over 4. So if I have just to draw a picture to kind of illustrate that point, if I'm going from time 0 to time capital T, my system will oscillate from my initial position, or it'll start with initial position and 0 velocity. It will go to its maximum velocity when it is at the equilibrium position. It will then go back to 0 at the other end of the, so this is like the negative a, or sorry, this is our positive a amplitude. That's our position, not our time. So this is a time versus position graph. But our position that we'd be at is going to be at A, and our velocity is going to be 0 when we're at position A. This is going to be at position x equals 0 when we are at our maximum. And then we are back at our minimum, or their 0 point, that's when we are at x is equal to negative a. Again, these are not time values. These are position values. I'm just drawing them to point out that at this time, we are at position x is equal to negative a, or x is equal to positive a, or x is equal to 0. So don't confuse the two. Now, I'm going to erase these just so it gets less chance of confusing you on this. But as I go, I'm going to go from a 0 velocity up to a maximum positive velocity, down to 0 velocity, and then I'm going to go down to my negative velocity, and then back to 0 velocity when I reach my my starting point again. So this is my capital T. I kind of didn't scale it correctly. So my capital T period will be where I'm at 0 velocity, and also when I am at time t equals 0, I will be at 0 velocity. But there's another point that I'm at 0 velocity in between, and that happens at time capital T over 2. So that's my halfway point in the motion. So when I start at the maximum amplitude, I go through equilibrium position, which will happen at t over 4. I will go to 0 velocity again, and that happens when I'm at my negative amplitude, and then I go back through my equilibrium position, which will happen at 3t over 4, and then back where I'm maximum velocity, and then I go back to my starting point, the maximum amplitude, which is my 0 velocity point again. So if you see this, you can probably think that this is a sine function, right? And that's true. So what we have is now a v of t is equal to sine of theta, just like we started before. Sine of theta, again, only goes between 0 and 1, and so we're going to need to get some way of expressing that maximum velocity. If you remember from the previous video, I said something about a top-down view and a side view of a circular object rotating circularly, but it also turns out that my maximum velocity Vmax is going to be equal to r times omega. And we said that that was equal to the amplitude times omega. So if I want to express my my velocity Vmax, I can express it as amplitude times omega. So I have v of t, my velocity function, is equal to a times omega times sine of theta. And again, we can't have a theta there. It needs to be an omega times t instead of a theta, because omega times t is equal to theta. And I need to have a time in my equation, otherwise it's not a function of time. So I get v of t is now equal to a times omega times sine of theta. There's one big issue here that we're missing though, and that is if I start off at my maximum amplitude, right now this is a diagram of my spring, and I start off here, maybe I've stretched my spring and so it's going way, way out to here to positive a. If I, and to the right will be plus x. If I start this system from rest, I let it go, it will begin to accelerate, but the force of the spring is in the opposite direction of positive. So my F spring force will be to the left. And so that means that we need a negative sign out front of our equation, because our velocity, if I stretch it, should start off negative. And I have negative a omega will give me a negative velocity. And then if I put the, if I think about it, maybe starting at the positive or the other amplitude, so minus a, if I start off here at minus a, what's going to happen is my spring force is going to push it in the positive direction. But my amplitude is minus a, and so I need negative a omega sine theta to make a positive velocity. So this equation here, v of t is equal to minus a omega sine theta, is really important. And I forgot to replace my theta with an omega times t. So this is our good equation that we want to use for our velocity a lot of times. There's one final equation that we need to get a hold of, and that is our acceleration function. So let's go ahead and take care of that, and then we'll be pretty much done. So for my acceleration, the place that we usually start when we talk about accelerations is our Newton's second law. So Newton's second law says that our force, or our net force, is equal to mass times acceleration. And here for this object, or this system, our net force is going to be acting on the mass m, that block that I had drawn in my pictures, and the acceleration is the acceleration function of time, a of t. But f is a weird thing. It is a position, or a position-dependent function. And so we'll kind of exploit that to get at our acceleration equation. Okay, so if I solve this equation for a, I would get a as a function of t is equal to the force, the net force, divided by m. But the only force that's acting in a simple harmonic oscillator is my spring force. So that is going to be a k times x divided by m. So then I'm going to just rearrange this equation. I'm not going to actually change it any. I'm just going to make it look slightly different. I get k times m times x, right? But this x is not just any x. It is x as a function of t. So my acceleration function, a of t, is equal to k divided by m times my x function, which you said was a times cosine of omega t. Wow, that was pretty easy. What else do we need to do? K and m, let's get rid of those. Remember, k over m is actually going to be the same thing as the square root of k over m squared. And that's really not changing anything. I'm just calling k over m the square root of k over m squared. But if I remember from previous videos, omega is also equal to the square root of k over m for simple harmonic oscillators, and for most oscillators as well. And so what I get then is a times omega squared times cosine of omega t. So that's awesome. That works out. Let's just check some things out to make sure it works. So here's my spring system. I start off at negative a maybe, go to positive a, and there's a 0 point in between. So if I have this thing stretched out to that positive a direction or distance, and I look at my force of my spring, it's going to be negative. So that would cause a negative acceleration. So at time t equals 0 for a stretch spring, my acceleration should be in the negative direction. If I am starting at negative a, my force will be to the right, which will be positive. Again, this is all assuming that plus x is to the right. And so here what I have is a sign issue, that if I plug in 0 into my acceleration function, and I say I'm stretching this thing out to positive a, and I plug in 0, I will get a positive acceleration, but my force will not cause a positive acceleration. It's in the opposite direction. So we'll just toss a negative sign out front. And so my acceleration function is a of t is equal to minus a omega squared times cosine of omega t, and it will work for either position. If I am at position A, you've already seen that. If I'm at position negative A, then I would have a positive acceleration because my force is pointing in the positive direction, and so I'd have negative times negative A, which becomes positive A omega squared cosine of omega t, which is a positive acceleration. So these are the equations of motion. I will kind of write them one more time to summarize them. They are x of t is equal to a cosine of, and I'm going to here put in the equations used on your equation sheet for AP. 2 pi f is our omega, t is our time. I would have v as a function of t is equal to minus a times omega of sine 2 pi f times time. And then I would have my acceleration function, a of t, is equal to minus a times omega squared cosine of 2 pi f times t. And that's it. So you might need these equations. For sure, the x of t equation will come into play. The v of t and the a of t, kind of unlikely that you will see them in the AP exam, but still it's good to know them in case it does come up, because it is something that certainly can be asked of you. So that's all I wanted to talk about in this video about our equations of motion. I have one more video where I will talk a little bit about pendulums, simple pendulums, and then from there we will be done with our talk about harmonic oscillators. Again, this should help you out with some of the weird stuff you've seen and probably couldn't do on those practice exams. So until next time, we will see you later.